For decades, scientists believed they understood how our universe began. A single point, a massive explosion, the birth of everything. But what if they were wrong? What if the Big Bang wasn't a beginning at all, but the consequence of something far stranger? What if right now you and I, and everything we've ever known, are trapped inside the belly of a cosmic beast? What time is it where you're listening? However late or early, you're exactly where you need to be. Tonight, we're diving into a mind-bending possibility that our entire universe exists inside a black hole. And if you're curious enough to follow this journey, maybe drop a like, share a thought below, or just settle in. Let's begin. So, what does this actually mean? Let me walk you through it. Because once you understand, you'll never look at reality the same way again. The idea is this: our entire universe, with its billions of galaxies, stars, planets, and yes, you listening right now, all of it might be contained within a black hole. Not a black hole in our universe, but a black hole from another universe, a universe with more dimensions of space than ours. From the outside looking in from that higher dimensional reality, it appears as an ordinary black hole, just another collapsed object. But from the inside, from our perspective, it's an entire cosmos, a pocket of space with its own laws of physics, its own time expanding and evolving independently. Now here's where things get really strange. What we call the Big Bang might not have been an absolute beginning at all. Instead, it could have been the moment when the event horizon of this massive black hole formed. Think about what that means. From outside the black hole, in that parent universe, a star collapsed. From their perspective, it happened quickly, maybe in seconds. But inside, due to extreme time dilation, that single moment stretched into 13.8 billion years. One instant outside equals the entire history of our universe inside. Time itself is so warped near a black hole that what looks like a fraction of a second from the outside becomes eons from within. This actually explains something that's puzzled cosmologists for decades. Why did the Big Bang happen everywhere at once? How could the entire universe begin simultaneously in all directions? If you think of the Big Bang as an explosion at a point, it doesn't make sense. But if the Big Bang was actually the formation of an event horizon, then it didn't happen at a point in space. It was the creation of space itself. The event horizon formed all at once, and from our perspective, inside it appears as though the universe exploded into existence everywhere simultaneously. There was no center, no edge, just sudden expansion in all directions at once. Now, let's talk about the edge of our universe. We have what astronomers call the cosmic horizon, the limit of what we can observe. Light from beyond that boundary simply hasn't had time to reach us yet in the 13.8 billion years since the Big Bang. Or has it? What if that cosmic horizon is actually the event horizon of the black hole we're inside? What if the reason we can't see beyond it isn't just about time and distance, but because light physically cannot escape from there? Think of it like this: the event horizon is the ultimate boundary, the point of no return. Just like the horizon you see when you look out at the ocean, the closer you try to get to it, the farther away it appears. You could walk toward the ocean's horizon forever and never reach it. The cosmic horizon works the same way. We can never reach it, never touch it, never cross it, because we've been inside this boundary since the very moment our universe began. We don't feel trapped because we've never known anything else. You have ever felt like you're living in an invisible box, like there are boundaries, you can't cross limits, you can't see but know are there? Maybe you're right. Picture a fish in a clear glass tank. The fish swims freely, explores every corner, lives its entire life, believing the water goes on forever. The tank has walls, definite boundaries, but the glass is transparent. The fish can't see it. It only discovers the limits when it swims too far and bumps into something it can't understand. We might be that fish. Our universe might have walls, an event horizon surrounding us, like invisible glass defining the absolute edge of our reality. But we'll never swim fast enough to touch those walls. Light itself can't escape an event horizon, and nothing can travel faster than light, so we're forever confined without ever feeling confined. But why should anyone take this idea seriously? It sounds like science fiction. Here's why it actually makes sense when you look at the evidence. Our universe has characteristics that are remarkably similar to what we'd expect inside a black hole. First, space is curved. Einstein's general relativity taught us that mass bends space-time, and we've confirmed this through countless observations. The universe isn't flat in the simple sense. It curves, it warps, it follows the geometry that massive objects create. Check. Second time flows in only one direction. We move forward through time inexorably. We can't go backward, can't reverse entropy, can't undo what's been done. Everything marches toward the future. This is exactly what happens inside a black hole, where all paths lead inevitably toward the singularity at the center. In our universe, all paths lead inevitably toward the future. The arrow of time points one way only. Check. Third, we have an observational boundary we cannot cross. The cosmic horizon limits what we can see, just as an event horizon limits what can escape a black hole. No matter how powerful our telescopes become, there's a fundamental limit to how far we can observe. Check. There's more evidence. The cosmic microwave background, that faint afterglow from the early universe, is remarkably uniform. It's almost exactly the same temperature in every direction we look to, within 1 part in 100,000. This uniformity tells us that everything in the observable universe must have come from the same initial conditions, the same special point. That's precisely what we'd expect if our universe formed from the interior of a collapsing object in a higher dimension. And then there's cosmic inflation, that mysterious period right after the Big Bang, when the universe expanded exponentially in less than a trillionth of a second space, grew from smaller than an atom to larger than a galaxy. It sounds impossible, but consider this. It's similar to how an event horizon expands when a black hole swallows matter. The horizon grows, rapidly stretching to accommodate what's falling in. Could inflation be the same phenomenon, just viewed from the inside? If this hypothesis is correct, think about what it means. Everything we consider to be reality, the total sum of existence as we know it, would be just the interior of a single object in a larger cosmos. And there could be countless other universes inside countless other black holes. Every black hole in our own universe, and there are millions of them, might contain its own complete universe, with its own stars, its own galaxies, perhaps even its own life. And those universes might have black holes that contain universes of their own. It's nested realities, universes within universes, like Russian Matryoshka dolls, each one containing another layers upon layers, extending infinitely in both directions. Now I know this sounds insane, but consider the history of science. Every time we've discovered we're less central, less special than we thought, our understanding has leapt forward. We used to believe Earth was the center of everything, with the sun and stars revolving around us. Wrong. Then we thought the sun was the center of the universe. Wrong again. Then we believed the Milky Way galaxy was the entire universe, and everything else was just clouds of gas. Wrong once more. Each time we've been humbled, each time we've shrunk our sense of cosmic importance, we've gained deeper insight into how reality actually works. This might simply be the next step in that ongoing journey of discovery. And here's something crucial to understand. If we are inside a black hole, it doesn't mean we're in danger. It doesn't mean we're about to be crushed or destroyed. We've been here for 13.8 billion years already. The sun rose this morning, and it will rise tomorrow. Your life continues exactly as it always has. The only thing that changes is our understanding, our perspective on where we fit in the grand architecture of existence. When humanity discovered that Earth orbits the sun rather than the other way around, nothing physically changed. Life went on. We just knew something deeper, something truer about our place in the cosmos. This knowledge doesn't make the universe smaller or less meaningful. If anything, it makes existence more magical, more wondrous. We could be one bubble in an infinite foam of realities, each one as vast and complex as our own, each one containing beings who look up at their skies and ask the same questions we're asking right now. Whether or not you're inside a black hole tonight, you're still safe in your bed. Black hole or not, you still need your sleep. And honestly, there's something almost comforting about it, isn't there? That even the most destructive, mysterious forces in the cosmos might give birth to entire worlds of beauty and wonder. Let's pause here for a moment. Let those thoughts settle like dust after a storm. But here's the fascinating thing. Black holes themselves were once considered utterly impossible. Even the greatest minds in the science refused to believe they could exist. So how did this concept transform from wild fantasy into established fact? The journey is more dramatic than any fiction. Our story begins in 1783 with a man named John Michel. Michel wasn't a professional scientist. He was an English country clergyman, a parson who tended to his parish while nurturing a deep fascination with the heavens. One day, while pondering Newton's laws of gravity and the nature of light, Michel conceived a strange idea. What if he wondered a star could be so massive, so incredibly dense, that its gravitational pull would be strong enough to prevent even light from escaping? This was a radical thought for the 18th century. Scientists at the time knew that light traveled at a finite speed, though they hadn't yet measured it precisely. Michel reasoned that if gravity could slow a thrown stone or a fired cannonball, perhaps it could affect light as well. And if a star was heavy enough, maybe light simply couldn't escape at all. The star would still be there, massive and real, but completely invisible. A dark star, he called it, hidden against the black backdrop of space. Michel wrote about this concept, published his ideas, even presented them to the Royal Society. And then, nothing. Absolute silence. Nobody took him seriously. The idea was too bizarre, too far removed from common sense. How could light, which seemed to have no weight, be trapped by gravity? It violated everything people understood about the natural world. Michel died having no idea whether his speculation held any truth. 200 years would pass before science vindicated him completely. Fast forward now to 1915. The world was engulfed in the horror of World War I. But in the world of physics, a different kind of revolution was taking place. Albert Einstein published his general theory of relativity, and it fundamentally transformed everything humanity thought it knew about gravity. Before Einstein, gravity seemed straightforward. It was a force, an invisible pull between masses. The Earth pulls the moon, the sun pulls the Earth like invisible ropes connecting everything. But Einstein said no, that's not how it works at all. Gravity isn't a force pulling objects together. Instead, mass curves the fabric of space-time itself, and objects simply follow those curves. Imagine space-time as a stretched rubber sheet. Place a heavy ball on it, and the sheet dips, creating a depression. Smaller objects placed nearby will roll toward that depression, not because they're being pulled, but because they're following the natural slope of the curved surface. That's gravity. Mass doesn't attract mass. Mass bends space-time, and everything follows the geometry of that bending. This was revolutionary, and hidden within Einstein's elegant equations was an unexpected prediction. Under certain extreme conditions, space-time could curve so intensely that it would collapse into itself, creating a region where the curvature became infinite, a gravitational well so deep that nothing, not even light, traveling at 300,000 kilometers per second, could climb back out. The mathematics predicted what we now call black holes. But here's the twist that makes this story so human. Einstein hated this conclusion. He thought black holes were a grotesque misinterpretation of his beautiful theory. Nature, he firmly believed, would never allow something so extreme, so violent, so ugly to actually exist. It offended his sense of cosmic elegance. Then came December 1915, just weeks after Einstein's publication. On the Eastern Front of World War I, a German physicist named Karl Schwarzschild was serving in the army. Picture the scene: trenches, artillery fire, soldiers dying in the mud. And in whatever quiet moments he could steal by flickering candlelight in a dugout, Schwarzschild was working through Einstein's equations. In January 1916, Schwarzschild sent Einstein a letter. He'd found it, an exact solution to the field equations. He'd calculated precisely what would happen if you compressed enough mass into a small enough space. At a certain critical radius, something extraordinary occurred. A boundary would form in the fabric of space-time itself. Cross that boundary, and you could never return. Everything inside would be drawn inexorably inward toward infinite density. Schwarzschild had discovered the event horizon, the point of no return. Einstein was stunned. This man in the middle of a war zone, surrounded by death and chaos, had solved problems Einstein himself hadn't fully worked out. The mathematics was perfect, undeniable, but tragedy followed discovery. Schwarzschild never lived to see the impact of his work. He contracted an illness at the front, probably pemphigus, a painful autoimmune disease. In May 1916, just 4 months after his breakthrough, Karl Schwarzschild died. He was 42 years old. He never knew that his name would become permanently attached to one of the most important concepts in astrophysics, that the Schwarzschild radius would be taught in universities for centuries to come. Have you ever believed something absolutely only to discover you were completely wrong? That's how Einstein felt. Even geniuses learn hard lessons. Despite Schwarzschild's flawless mathematics, Einstein spent the next 2 decades arguing against the physical reality of black holes. He wrote paper after paper, attempting to prove they couldn't actually form in nature. Nature does not permit such extreme things, he insisted. And because Einstein was Einstein, because his name carried such weight, most of the scientific community sided with him. Black holes became a mathematical curiosity, an interesting theoretical toy, but surely not something that existed in the real universe. Surely nature had some mechanism, some safety valve, to prevent such cosmic absurdities. Einstein was wrong. The universe, as it turns out, doesn't care what we find beautiful or disturbing. The turning point came in 1964. Astronomers detected an unusually powerful source of X-rays emanating from the constellation Cygnus. They designated it Cygnus X1. When they studied it more carefully, they discovered something deeply strange: a visible blue supergiant star, clearly observable through telescopes, orbiting around something completely invisible. Whatever that invisible object was, it had a mass roughly 15 times greater than our sun, yet it emitted no light whatsoever. It was pulling material from its companion star, and as that material spiraled inward, it heated to millions of degrees, shrieking X-rays into space, before vanishing forever across an invisible boundary. Every measurement, every observation matched the theoretical predictions for a black hole with stunning precision. But old beliefs die hard, especially in science. In 1971, Stephen Hawking, the brilliant young physicist who had spent years studying black holes, theoretically made a public bet with Kip Thorne. Hawking bet that Cygnus X1 was not a black hole. Why would he bet against his own field of research? Because part of him hoped black holes didn't actually exist. If they turned out to be fantasy, at least his life's work hadn't been wasted on impossibilities. By 1990, the evidence had become overwhelming. Multiple independent observations all pointed to the same conclusion. Hawking publicly conceded the bet, sending Thorne a formal, written admission of defeat. Cygnus X1 was real. Black holes existed. And with that acknowledgement, everything changed. Before 1967, scientists had called them frozen stars, because from an outside observer's perspective, time appears to freeze at the event horizon. But that name lacked drama, failed to capture anyone's imagination. Then physicist John Wheeler coined a new term during a lecture, black hole. It was vivid, memorable, slightly ominous. The name stuck immediately, and with that simple rebranding, black holes exploded into popular culture. Suddenly, everyone wanted to know about these cosmic monsters that devoured light itself. Schwarzschild solved the deepest mysteries of space-time in a trench surrounded by war, like writing poetry in a hurricane. That's the power of human curiosity. Think about what Schwarzschild's story really means. Here was a man in the worst circumstances imaginable: war, consuming everything around him, death everywhere, and he chose to spend his final months contemplating the fundamental structure of reality. Not survival, not fear, but the cosmos, the mathematics of curved space-time and singularities. Science transcends borders, transcends war, transcends even our own mortality. And Einstein's stubbornness, it teaches us something profound too. Even the greatest genius of the 20th century let personal aesthetics cloud scientific judgment. He wanted the universe to be harmonious and beautiful, and black holes seemed violent and ugly. But nature doesn't ask our permission. The universe is what it is, regardless of whether we find it pleasing. Einstein hated black holes for 20 years. But the universe doesn't ask permission from anyone. So black holes went from impossible fantasy to confirmed reality in less than a century. But that just raises deeper questions. What exactly are these things? Why can't anything escape them? What happens at their heart? Let's go deeper. Let's step right to the edge and look into the abyss itself. So now we know black holes exist. We know they're real, confirmed by observation and mathematics. But what exactly are they? What makes them so different from everything else in the universe? Let's pull back the curtain and look directly at the anatomy of these cosmic beasts. At the heart of every black hole discussion is something called the event horizon. Despite its dramatic name, the event horizon isn't a physical surface. You can't touch it, can't stand on it, can't see it directly. It's a mathematical boundary, an invisible line in space that marks the point of no return. Here's what makes it special. It's the location where the escape velocity, the speed you'd need to break free from the black hole's gravity, exceeds the speed of light. Think about the escape velocity for a moment. To leave Earth's surface and reach space, a rocket needs to achieve about 11 kilometers per second. That's Earth's escape velocity. For the moon, it's lower, just 2.4 kilometers per second, which is why the moon has no atmosphere. Gas molecules, moving at normal temperatures, can simply drift away into space. But at a black hole's event horizon, the escape velocity is greater than 300,000 kilometers per second. That's faster than light. And since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever come back out. Nothing. Not matter, not energy, not information, not even time itself. From far away, looking at a black hole from a safe distance, something strange happens to time near the event horizon. Imagine watching a clock fall toward a black hole. As it gets closer and closer to that boundary, the clock appears to tick more and more slowly. It's not an illusion. Time itself is actually running slower there, due to the intense gravitational field. As the clock reaches the event horizon, from your distant perspective, it appears to freeze completely. The clock stops. The falling object appears suspended motionless, preserved at that boundary forever. This is why early scientists called them frozen stars. But here's the weird part. If you were riding along with that clock falling toward the black hole yourself, you wouldn't notice anything strange at all. Your watch would tick normally. Time would feel completely ordinary to you. You'd pass right through the event horizon without even noticing the moment it happened. No flash of light, no warning sign, no sensation of crossing anything. From your perspective, time flows normally. It's only to the outside universe that you appear frozen. The event horizon is like a decision you can't take back. Once you cross it, every path forward leads the same direction. There's no going back ever. At the center of a black hole lies something even stranger, the singularity. This is where all the mass of the black hole is concentrated, where gravity becomes so intense that space-time itself curves infinitely. At the singularity, density becomes infinite. The curvature of space-time becomes infinite. Our physics, our mathematics, everything we know simply breaks down and stops working. The equations return infinity, which in science usually means we don't understand what's really happening there. It's like dividing by zero. The math can't handle it. Some physicists think the singularity isn't truly infinite, that when we finally develop a complete theory of quantum gravity combining quantum mechanics with Einstein's relativity, we'll discover that something else happens at the center. Maybe matter reaches some maximum density, but doesn't truly become infinite. Maybe there's a quantum core incredibly small, but not actually a point. But for now, the singularity remains hidden behind the event horizon, protected by what physicist Roger Penrose called cosmic censorship. Nature seems to hide these impossible infinities from the rest of the universe, keeping them locked away where they can't break the laws of physics everywhere else. Now let's talk about time dilation in more detail, because it's one of the most mind-bending aspects of black holes. The closer you get to a massive object, the slower time flows relative to someone farther away. We've actually measured this effect here on Earth in laboratories. Atomic clocks at sea level run slightly slower than identical clocks on mountaintops. The difference is tiny, just billionths of a second, but it's real and measurable. GPS satellites have to account for this effect constantly, or they'd give you the wrong location. Near a black hole, this effect becomes extreme. Hover just outside the event horizon, and time for you would slow to a crawl compared to the rest of the universe. If you could somehow survive there for what felt like an hour to you, you might return to find that millions of years had passed everywhere else. But here's the crucial thing: you wouldn't feel time moving slowly. From your perspective, everything would seem normal. It's only when you compared notes with the outside universe that you discover the difference. Not all black holes are the same. They come in different sizes, different types, formed through different processes. Stellar black holes are the most common, formed when massive stars, at least 3 times more massive than our Sun, reach the end of their lives and collapse. These black holes typically range from about 3 to 50 times the mass of the Sun. There are probably hundreds of millions of them scattered throughout our galaxy alone. Then there are supermassive black holes, the giants that lurk at the centers of most large galaxies. These monsters weigh millions or even billions of times more than our Sun. The one at the center of our own Milky Way galaxy, called Sagittarius A star, has a mass of about 4 million suns. The one at the center of the galaxy, M87, which we'll talk about later, weighs 6.5 billion solar masses. How these supermassive black holes formed is still something of a mystery. They're too big to have come from individual stars. They must have grown over billions of years, either by merging with other black holes or by continuously feeding on gas and dust. There are also intermediate mass black holes ranging from hundreds to 1,000 of solar masses. These are harder to find and less well understood. Scientists think they might form when stellar black holes merge together, or possibly in the dense centers of star clusters, where multiple stars collapse simultaneously. And then there are primordial black holes, which are purely hypothetical at this point. These would have formed in the extremely early universe, right after the Big Bang, from density fluctuations in the primordial soup of matter and energy. If they exist, they could be any size from microscopic to massive. Some scientists have even proposed that primordial black holes might actually be dark matter, that mysterious substance that makes up most of the mass in the universe, but doesn't emit light. Most black holes aren't just sitting still in space. They're spinning, sometimes incredibly fast. These are called Kerr black holes, named after physicist Roy Kerr, who solved Einstein's equations for rotating black holes in 1963. When a massive star collapses to form a black hole, it conserves its angular momentum. Since the star was probably rotating before it collapsed, and now all that mass is concentrated in a much smaller space, the rotation speeds up dramatically. It's like a figure skater pulling in their arms during a spin. A spinning black hole does something remarkable. It drags space-time around with it. This effect is called frame dragging. Imagine stirring honey with a spoon. The honey near the spoon gets dragged around, pulled along by the spoon's motion. A rotating black hole does the same thing to space-time itself. Close to the black hole, space itself is rotating, pulled around by the black hole's spin in a region called the ergosphere. Just outside the event horizon, space-time is being dragged so forcefully that nothing can stand still. Even if you fired your rockets at full power, you'd still be pulled around in the direction of the black hole's rotation. This effect has actually been confirmed in miniature form by NASA's Gravity Probe B satellite, which detected frame dragging around Earth itself. Earth's rotation drags space-time around it too, just by an incredibly tiny amount. For rotating black holes, the singularity at the center might not be a point at all. It might be a ring, a circle of infinite density, rather than a point. This opens up even stranger possibilities in the mathematics, though we have no way to observe what's actually happening in there. Now, black holes don't just sit in empty space. They're often surrounded by swirling disks of gas and dust called accretion disks. When matter falls toward a black hole, it doesn't usually fall straight in. It has some sideways motion, some angular momentum, so it spirals inward instead, forming a flat disk that orbits the black hole. As particles in this disk rub against each other, friction heats them up. And we're not talking about warm, we're talking about millions of degrees hot enough to emit intense X-rays and gamma rays. This is actually how we detect most black holes. The black hole itself is invisible, but the accretion disk around it blazes brilliantly. Cygnus X1, the first confirmed black hole, was discovered because astronomers detected powerful X-rays coming from the superheated gas spiraling into it. Within the accretion disk, light does something extraordinary. Some photons, particles of light, get caught in orbits around the black hole. They circle once, twice, 3 times or more before either falling in or escaping outward. This creates what are called photon rings, nested circles of light at different distances from the event horizon. Each ring represents light, that's orbited the black hole a different number of times. We've actually photographed these photon rings, as we'll see shortly. Some rotating black holes produce jets, narrow beams of particles and energy that shoot out from the poles at nearly the speed of light. These jets can extend for thousands of light years, far longer than entire galaxies. They carry enormous energy, sometimes more than the entire galaxy they're part of. The mechanism that produces them involves the black hole's spin powerful magnetic fields and the accretion disk working together in ways we're still trying to fully understand. These jets can influence star formation across vast regions of space, shaping the evolution of galaxies themselves. So, why exactly can't light escape from a black hole? Let me put it simply. Light is the fastest thing in the universe, traveling at 300,000 kilometers per second. Nothing goes faster. To escape from Earth's gravity, you need to reach about 11 kilometers per second. That's escape velocity. To escape from the sun's surface, you'd need to reach over 600 kilometers per second. The more massive an object and the smaller its radius, the higher the escape velocity becomes. At a black hole's event horizon, the escape velocity exceeds the speed of light. Since nothing can go faster than light, nothing can escape. But here's the key insight. It's not that light is being sucked in like water down a drain. It's that space-time is so curved, so warped, that every possible direction, every possible path leads inward. There is no outward. Inside the event horizon, all roads lead to the singularity. It's not about being pulled, it's about geometry. Space itself is curved in such a way that escape becomes geometrically impossible. There's one more effect I should mention, and it has possibly the most amusing name in all of physics spaghettification. The scientists who named this were clearly having fun, but don't let the playful name fool you. It describes something genuinely terrifying. Imagine falling feet first toward a black hole. Your feet are closer to the black hole than your head, so they experience stronger gravity. As you get closer, that difference becomes more and more extreme. Your feet are being pulled harder than your knees harder than your waist harder than your chest. The gravitational gradient stretches you, pulling you longer and thinner, like taffy being pulled, like spaghetti being formed. Hence, spaghettification. For smaller black holes, stellar mass ones, this stretching would rip you apart long before you reached the event horizon. You'd be torn into atoms then, into subatomic particles stretched into a thin stream of matter, spiraling inward. But for supermassive black holes, the ones millions or billions of times more massive than the sun, something different happens. Because they're so large, the event horizon is very far from the center, and the gravitational gradient there is actually quite gentle. You could cross the event horizon of a supermassive black hole completely intact, feeling nothing unusual. The spaghettification would only come later, as you fell inward toward the singularity. Not that it makes much difference in the end. Spaghettification scientists had fun naming it, but trust me, this isn't a buffet you'd want to attend. A black hole is like a cosmic drain. Everything spirals in, nothing comes back out. But unlike a drain, it doesn't lead anywhere. Or does it? So that's what black holes are. Regions where gravity has won completely, where space-time curves back on itself. where the normal rules break down, event horizons, marking points of no return, singularities where physics fails, time dilation that stretches seconds into eons, accretion disks blazing with the death screams of infalling matter, jets shooting across cosmic distances. And at the heart of it all, a mystery we still can't fully solve. But black holes aren't just objects of scientific study. They've captured human imagination for far longer than they've been confirmed to exist. Let's step back from the equations and look at how these cosmic monsters have haunted our art, our stories, our deepest fears and fascinations. Black holes aren't just science. They're symbols, metaphors, mirrors for our deepest questions about existence. And strangely, artists and writers sensed them, dreamed about them, long before scientists proved they were real. Consider Edgar Allan Poe, the master of Gothic horror, writing in 1848, more than a century before black holes were confirmed. Poe wrote a prose poem called Eureka, subtitled An Essay on the Material and Spiritual Universe. In it, he described the cosmos in remarkably prescient terms. He envisioned the entire universe collapsing back into itself, all matter and energy rushing inward toward a single point crushed into nothing before exploding outward again in an endless cycle of creation and destruction. Now, Poe wasn't doing physics. He had no equations, no telescopes, no data. His vision wasn't scientifically accurate in its details. But there's something hauntingly similar to the concept of a singularity. In his words, this idea of everything collapsing into an infinitely dense point. Poe was feeling his way towards something that mathematics wouldn't describe for another 70 years. He intuited the possibility before science could prove it. The poet saw what the physicist had yet to calculate. This happens sometimes in human creativity. Artists sense truths that science later confirms not through reason or measurement, but through imagination, through metaphor, through some deep pattern recognition that operates below conscious thought. Jump forward to the 20th century. After Einstein published his theory of relativity, surrealist artists became fascinated with the implications. Salvador Dalí, perhaps the most famous surrealist painter, created works that explored warped space and shattered time. His painting, The Persistence of Memory, with its melting clocks, captures something essential about relativity, that time isn't absolute, isn't fixed, but bends and flows and changes depending on where you are and how fast you're moving. Dalí painted space that curves back on itself, infinity swallowing itself, objects distorted beyond recognition. He wasn't illustrating physics textbooks. He was exploring the emotional and philosophical implications of Einstein's universe. What does it feel like to exist in a cosmos where time is relative, where space can curve, where the solid and permanent becomes fluid and strange? Dalí's melting clocks and impossible geometries tried to answer that question through art. Science and art were asking the same questions, just in different languages. Then came 1967, when physicist John Wheeler coined the term black hole during a lecture. Before that, scientists had been calling them frozen stars, or collapsed objects, or Schwarzschild singularities. These names were accurate, but uninspiring. They didn't capture the imagination. They didn't make you feel anything. Black hole, though, that name worked. It was mysterious, slightly ominous. It suggested an absence, a void, something that swallows and doesn't give back. The name was catchy, dramatic, easy to remember, and easy to visualize, even if you didn't understand the physics. And that simple act of naming that bit of marketing genius changed everything. Suddenly, everyone wanted to know about black holes. The name made them accessible, gave them personality. Scientists had stumbled onto something advertisers have always known: the right name matters. Call something a gravitationally collapsed object, and people's eyes glaze over. Call it a black hole, and suddenly they lean forward, paying attention. From that moment on, black holes exploded into popular culture. They showed up everywhere: science fiction novels, movies, television shows, comic books, songs, poems. They became cultural shorthand for mystery, for danger, for the unknown. To say something was like a black hole meant it was inescapable, consuming, perhaps incomprehensible. In 1979, Disney produced a movie literally called The Black Hole, a dark science fiction film about a ship approaching a massive black hole and the mysterious spacecraft orbiting it. It was eerie, unsettling, more horror than adventure. The black hole in the film wasn't just a scientific phenomenon. It was almost a character, a presence, something with agency and intention. Then came 2014 and Christopher Nolan's Interstellar. This film took black holes seriously in a way no movie had before. Nolan hired Kip Thorne, one of the world's leading experts on relativity and black holes, who would later win the Nobel Prize, as a scientific consultant. Thorne didn't just advise. He provided the actual equations describing how light behaves near a rotating black hole. The result was Gargantua, the most scientifically accurate depiction of a black hole ever put on screen. Audiences saw the accretion disk blazing with superheated matter. They saw gravitational lensing, the way the black hole's gravity bends light from the disk, both above and below it, creating that strange doubled appearance. They saw the photon ring light that orbits the black hole before escaping. They experienced time dilation, watching one character age by decades, while another, near the black hole, ages by only hours. For the first time, the general public saw what a black hole would actually look like: not artist's imagination, but mathematics made visual. And it was more beautiful, more strange than anyone had imagined. Do you fear black holes? Or does the mystery fascinate you? Maybe both. That's the beauty of the unknown. It pulls us toward it, even when we're afraid. Why are we so drawn to black holes? Part of it is that they represent something beyond our control, beyond our ability to fight or resist. Modern life gives us the illusion of control. We can cure diseases, predict weather, communicate instantly across continents, fly through the air. But a black hole, it's a force of nature, so absolute, so overwhelming, that all our technology, all our cleverness, all our will becomes irrelevant. There's something almost refreshing about that. It reminds us that we're still small, still vulnerable, still living in a universe vastly more powerful than we are. Black holes also tap into our natural curiosity about what lies beyond boundaries. What's on the other side of the event horizon? What happens at the singularity? These are questions we can't answer through direct observation, and that makes them irresistible. It's the same impulse that makes us wonder what happens after death, what lies beyond the edge of the universe, whether we're alone in the cosmos. Black holes are the ultimate locked door, and we can't help but wonder what's inside. There's also something thrilling about them, in the same way horror movies are thrilling. We can contemplate black holes from safety. We can imagine falling into one, being stretched and torn and crushed, but we know it's not actually happening. It's danger. At a distance, terror we can control by simply looking away. We're wired to find that combination of fear and safety compelling. Black holes are like the ending of a good mystery novel. You're afraid to know the truth, but you absolutely cannot stop wondering. Interestingly, black holes appear in mythology too, even though ancient cultures had no telescopes or physics. In Hindu mythology, the god Shiva performs a cosmic dance, the Tandava, which represents the cycle of creation and destruction. Shiva creates the universe and destroys it over and over in an eternal rhythm. There's something remarkably similar to black holes in this image, objects that destroy but also potentially create. Matter falling into a black hole is destroyed as far as our universe is concerned, but perhaps, as some theories suggest, it creates something new somewhere else. Indigenous cultures around the world have myths about devourers of light, cosmic serpents, or great beasts that swallow the sun or stars. These stories, passed down for thousands of years, seem to anticipate black holes in metaphorical form. Ancient humans, looking up at the night sky, intuited that there might be places where light goes to die, even if they couldn't explain it scientifically. This suggests something profound. Maybe our fascination with black holes isn't new at all. Maybe we've always sensed them in the same way we've always sensed that the universe is bigger and stranger than our immediate experience. Modern science simply gave names and equations to something humans have always felt. This story exists because black holes never stop fascinating us. If we understood them completely, they'd lose their magic. Mystery is essential. So, black holes live in two worlds: the world of science, of equations and observations and measurements, and the world of imagination, of fear and wonder and metaphor. They're both real physical objects and powerful symbols. They're monsters and marvels. They're the universe at its most extreme, and humans at their most curious. They remind us that the cosmos doesn't exist only in textbooks and telescopes. It exists in poems and paintings, in dreams and nightmares, in every story we tell about what might lie beyond the edge of what we know. And then, in 2019, something extraordinary happened. Humanity did something that seemed impossible. We pointed our instruments at the heavens and actually saw a black hole. Not indirectly, not through mathematical inference, but saw it, captured its image, photographed the invisible. Let's talk about that moment, because it changed everything, from imagination to reality. In 2019, humanity accomplished something that seemed genuinely impossible. Just decades earlier, we photographed a black hole. We captured an image of the invisible. But how do you photograph something that by definition doesn't emit light? How do you see something designed by the laws of physics to be unseen? The answer required building one of the most ambitious scientific instruments ever conceived, the Event Horizon Telescope. The Event Horizon Telescope isn't a single telescope. It's a network, a collaboration of 8 radio telescope observatories scattered across 4 continents. There are telescopes in Arizona, in Hawaii, in Chile, in Spain, in Mexico, at the South Pole. Each one operates independently, but during observation campaigns, they all point at the same target, simultaneously recording radio waves from the same cosmic source. The technique is called interferometry. Instead of building one impossibly large telescope, you synchronize multiple smaller telescopes and combine their data. When you link observatories across the entire planet, you essentially create a virtual telescope dish as large as Earth itself. The resolution this provides is almost incomprehensible. With the Event Horizon Telescope, you could theoretically read a newspaper in New York while standing in Paris. You could see an orange on the surface of the moon. This extreme precision is absolutely necessary because black holes, despite being enormous, appear incredibly small from Earth. The supermassive black hole at the center of our own galaxy is 4 million times more massive than the Sun, but is also 27,000 light years away. From here, it appears smaller in the sky than a single atom held at arm's length. To photograph something that small and that far requires a telescope the size of a planet. The team chose two primary targets. One was Sagittarius A star, the supermassive black hole at the heart of the Milky Way, our home galaxy. The other was an even more massive beast at the center of a galaxy called Messier 87, or M87 for short. M87's black hole won the race to be first photographed, and for good reason. It's absolutely gargantuan, weighing 6.5 billion times the mass of our Sun. It's 55 million light years away, which sounds impossibly distant, and it is. Light from M87 has been traveling toward us since before humans existed, since before primates evolved, since long before the age of dinosaurs. But despite that distance, M87's black hole appears large enough in the sky to photograph because it's just so monumentally huge. It also sits at a favorable angle relative to Earth, giving us a clear view of its accretion disk. The observation campaign began in 2017. Multiple nights of coordinated observations, all 8 telescopes recording simultaneously, generating an absolutely staggering amount of data. We're talking about petabytes of information, so much that it couldn't be transmitted over the internet. Hard drives had to be physically shipped from each observatory to central processing facilities. Then came months of analysis, of combining the data, of running it through sophisticated algorithms to construct an actual image from radio waves recorded across the planet. On April 10th, 2019, the team held simultaneous press conferences around the world, and they revealed it. The first photograph of a black hole. The image shows a glowing orange-red ring surrounding a dark center. That dark region isn't the black hole itself. It's the shadow of the black hole, the silhouette of the event horizon against the bright material behind it. The ring of light is the accretion disk, superheated matter, spiraling toward oblivion at a significant fraction of light speed, so hot it glows in radio wavelengths. But there's something else visible too. The light isn't uniform. It's brighter on one side than the other. That's because of the black hole's rotation and something called relativistic beaming. Matter on the side moving toward us appears brighter, while matter moving away appears dimmer. What makes the image so striking is how the light bends. Gravity warps the path of photons traveling near the black hole. Light from behind the black hole curves around it, appearing both above and below the dark center. This gravitational lensing creates that distinctive ring shape. The bright circle we see isn't just the disk in front of the black hole. It's also light from the disk behind the black hole, bent around by gravity and focused toward our view. When you look at that photograph, do you feel something shift inside you? That's the moment humanity touched what was once impossible. The image confirmed Einstein's predictions with stunning accuracy. A century after he published his general theory of relativity, 70 years after his death, his equations were still predicting reality with perfect precision. The shape of the shadow, its size relative to the black hole's mass, the way light bent around it, all of it matched the mathematics exactly. Einstein never believed black holes truly existed. He fought against the idea for decades, but his equations knew better than he did. Within that bright ring are nested structures called photon rings. Some light orbiting the black hole completes one circuit before escaping toward us. Other photons complete 2 orbits, 3 orbits, even more, before breaking free. Each orbit creates a slightly different ring nested within the others, like a cosmic Russian doll. Future observations with even better resolution might be able to distinguish these individual rings. Here's something remarkable about photon rings. Each one carries light from a different time. Photons that orbited once left the accretion disk at one moment. Photons that orbited 3 times left at an earlier moment and spent more time looping around before escaping. By analyzing these rings separately, scientists could potentially see the black hole at different moments in its past, watching matter fall in like frames in a movie. The black hole becomes not just a subject for photography, but for cinematography. The philosophical significance is profound. For the first time in history, humanity observed an event horizon directly. We saw the boundary between what can be known and what cannot, between the universe we inhabit and the region forever cut off from it. We didn't see the black hole itself. That's impossible. We saw its absence, its shadow, the outline of where it exists by observing what it blocks and how it bends light around itself. It's like seeing wind. You can't see air moving, but you can see leaves rustling, trees swaying, dust spiraling. The wind reveals itself through its effects. Similarly, we can't see a black hole, but we can see how it affects everything around it. That photograph is evidence of the invisible, made visible through inference and brilliance. The image also became a symbol of what humanity can achieve through cooperation. Scientists from dozens of countries speaking different languages, from different cultures, worked together for years on this single project. The data was shared freely. The results were announced simultaneously, worldwide. In a fractured, divided world, the Event Horizon Telescope represented something pure, curiosity, transcending borders, knowledge pursued for its own sake, humanity unified by wonder. One face became associated with the achievement Katie Booman, a 29-year-old computer scientist who developed crucial algorithms for processing the Event Horizon Telescope data. A photograph of Katie, eyes wide with joy and disbelief, as the image first appeared on her laptop screen, went viral. She became for a moment the face of the project. What made this particularly significant was that Katie represented something new in science. She wasn't an astronomer or a physicist by training. She was a computer scientist bringing algorithmic and computational expertise to an astrophysics problem. She represented interdisciplinary collaboration, the breaking down of walls between fields. She also represented diversity in a field historically dominated by men, particularly older men. Science wasn't just old equations and old telescopes anymore. It was young minds, diverse perspectives, new approaches to ancient questions. Many scientists who worked on the project wept when they first saw the image. Some had devoted their entire careers to this goal, decades of work culminating in that single photograph. It was like climbing a mountain for 30 years and finally reaching the summit. The emotion was overwhelming. The public felt it too. The image circulated globally within hours. People who'd never thought about astrophysics shared it, talked about it, felt moved by it. Why? Because it represented human capability. We built an Earth-sized telescope. We coordinated across continents and time zones. We photographed something invisible, 55 million light years away. If we can do that, what else might we achieve? It's like the first photograph of Earth from the moon. Suddenly, we understood both how small we are and how capable we are. 3 years later, in 2022, the Event Horizon Telescope team released another image. Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. This one was technically more difficult to photograph because it's smaller and the material around it moves more quickly, changing from night to night. But they succeeded. Sagittarius A star is only about 4 million solar masses, tiny compared to M87's monster. It's also much closer, just 27,000 light years away. Just 27,000 light years. Still an incomprehensible distance, but practically next door in cosmic terms. This is our black hole, the one we orbit around the gravitational anchor of our entire galaxy. The image confirmed something astronomers had suspected: every large galaxy has a supermassive black hole at its center. These aren't rare cosmic oddities. They're fundamental components of galactic structure, perhaps even necessary for galaxies to form and evolve the way they do. It took 100 years from theory to photograph. Science doesn't rush, but when it arrives, it's worth the wait. Each photon ring visible in these images potentially contains information from different moments in time. The innermost ring shows the most recent light, while rings further out show light that escaped earlier but took longer paths orbiting the black hole, multiple times before reaching us. Scientists hope that future observations with even higher resolution will let them analyze each ring separately, essentially, watching a movie of matter falling into a black hole across time. This is just the beginning. The Event Horizon Telescope is being upgraded. More observatories are joining the network. Resolution will improve. We'll see these black holes in finer detail, perhaps even watching them change over time as they consume matter. We might observe other black holes building a catalog of images, showing how they differ. And this is still just the beginning of the story. Black holes hold more mysteries than what we've seen so far. We've looked at black holes from the outside. We've seen their shadows, their effects, their influence on the cosmos. But what if the wildest idea is actually true? What if we're not just observing black holes from a distance, but living inside one? What if our entire universe is the interior of a black hole? in some larger reality. We've seen black holes from outside, but what if we're already inside one? What if this universe is the interior of a black hole in a larger cosmos? In the next part of our journey, we'll dive deep into that possibility. But for now, as the night deepens, let your mind rest. When you close your eyes tonight, imagine that glowing orange ring light bending around the event horizon like gentle ripples on water. Picture it slowly, softly. The circle glows, then dims, then fades into darkness. And as it fades, you drift floating in space, where there are no boundaries, no horizons, only peace. No mathematics, no measurements, just the gentle pull of sleep, drawing you inward like gravity that doesn't crush but cradles. Sleep well. We've seen black holes from the outside. We've photographed their shadows, measured their mass-watched matter, spiral into their event horizons. But now, we're going to ask a much stranger question. What if we're seeing black holes from the inside? What if the universe we inhabit is itself contained within one? To understand this possibility, we need to talk about dimensions. Not the science fiction kind, but the mathematical kind, the geometry of reality itself. And that means we need to discuss one of the most ambitious theories in physics, string theory. You're probably used to thinking of the universe as having 3 dimensions of space. There's left and right, that's one dimension. Forward and backward, that's the second. Up and down, that's the third. Move along any combination of these 3 axes, and you can reach any point in space. Add time as a 4th dimension, and you have space-time, the 4-dimensional fabric that Einstein showed us bends and curves under gravity. But string theory says that that's not the whole story. According to string theory, the universe actually has 10 or 11 dimensions, depending on which version of the theory you're working with. 10 or 11, not 4. So, where are the other 6 or 7 dimensions? Hiding. The answer string theory gives is both elegant and strange. They're curled up. They're compactified, rolled into shapes so microscopically tiny that we can't perceive them directly. Imagine an ant walking on a garden hose. From far away, the hose looks one-dimensional, just a line. But if you're an ant on the surface, you discover there's another dimension. You can walk around the circumference of the hose. That circular dimension exists, but it's so small compared to the length of the hose that from a distance you don't notice it. String theory proposes that at every point in our 3-dimensional space, there are additional dimensions curled up into incredibly small shapes, smaller than atoms, smaller than protons, smaller than anything we can currently measure. These hidden dimensions are there, affecting the laws of physics, determining how particles behave and how forces work. But we experience them only indirectly through their effects on the dimensions we can see. Why would nature hide dimensions like this? In string theory, the fundamental building blocks of reality aren't point-like particles, but tiny vibrating strings of energy. The way these strings vibrate determines what kind of particle they appear to be: an electron, a quark, a photon. And crucially, the strings vibrate not just in the 3 dimensions we see, but in all the dimensions that exist. The extra dimensions shape how the strings can vibrate, which in turn determines the spectrum of particles and forces we observe. Without those hidden dimensions, the mathematics of string theory simply doesn't work. The equations need those extra dimensions to be internally consistent. Have you ever sensed there's something more than what you can see? Something just beyond perception? Maybe you're sensing dimensions we haven't learned to observe yet. Think of it like this: those hidden dimensions are like scent. You know a smell exists, you experience it, it affects you, it carries information, but you can't see it, can't point to where it is in space. It's there, real and measurable in its effects, but invisible to sight. The extra dimensions of string theory are similar, real, present, everywhere, affecting everything, but operating at scales or in ways our senses and instruments don't directly access. Now, string theory leads to something called brain cosmology. Brain is short for membrane, like a two-dimensional surface. In this framework, our entire three-dimensional universe might actually be a brain, a three-dimensional membrane floating in a higher dimensional space called the bulk. Imagine you're drawing on a piece of paper. You can move left or right, forward or backward along the surface of the paper. Those are your two dimensions. But you have no concept of up and down off the paper's surface because you're confined to the sheet. Now imagine that paper is floating in a room. The room has three dimensions, but you trapped on the paper only experience two. The paper is your brain. The room is the bulk. In brain cosmology, our universe is like that paper. We experience three dimensions of space plus time, but we're embedded in a higher dimensional bulk that might have additional spatial dimensions we can't access. We're stuck on our brain, unable to step off into the bulk, just as a drawing can't step off the paper. This idea has profound implications for black holes. If our universe is a three-dimensional brain in a higher dimensional bulk, then black holes might not be purely three-dimensional objects. They might extend into those extra dimensions. From our perspective, confined to our brain, we see a black hole as a three-dimensional object with an event horizon, an accretion disk, all the features we've discussed. But from a higher dimensional viewpoint, looking at our brain from outside, a black hole might look completely different. It might be a higher dimensional structure that intersects our brain, appearing to us as the three-dimensional black hole we observe. Here's where it gets really interesting. Some physicists have proposed that what we call the Big Bang, the beginning of our universe, might actually have been the formation of a black hole in a higher dimensional space. A star in that higher dimension collapsed, creating a black hole. From the perspective of beings in that higher dimension, they see an ordinary black hole, a region of curved space-time with an event horizon. But inside that black hole, the conditions were such that a pocket universe formed a bubble of space-time with its own geometry, its own laws. That pocket universe is our cosmos. From outside, looking in from the higher dimension, it's a black hole. From inside, living within it, it's an entire universe. Same object, two completely different perspectives. The reason we don't perceive these extra dimensions directly is that we're confined to our brain, to our three-dimensional slice of reality. Every particle we're made of, every force we experience, except gravity, is stuck on the brain with us. Photons can't escape into the bulk. Electrons can't venture off our three-dimensional surface. But gravity is different. In brain cosmology, gravity can leak into the bulk, can spread out into the higher dimensions. This might explain why gravity is so much weaker than the other fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force. They're all confined to our brain, concentrated in our 3 dimensions. But gravity spreads out into the bulk, diluting across more dimensions, which makes it appear weaker in our experience. If black holes are higher dimensional objects, they might serve as connections between different brains. Imagine multiple sheets of paper floating in that room we talked about earlier. A nail driven through several sheets would pierce them all, connecting them. A higher dimensional black hole might work similarly, creating a connection between our brain and other brains floating in the bulk. Matter that falls into a black hole on our brain might emerge in another brain, another universe, through what we perceive as a white hole, the theoretical opposite of a black hole that expels matter instead of consuming it. This is deeply speculative, of course. We have no direct evidence for extra dimensions or brains or the bulk. These are mathematical constructs that emerge from string theory, which itself remains unproven. The energies required to probe these scales directly are far beyond anything we can generate in particle accelerators. But the mathematics is consistent, elegant, and suggests possibilities that make the universe far stranger and larger than we typically imagine. Why can't we just see these extra dimensions? Why can't we step off our brain and explore the bulk? The answer lies in how physics works at different scales. The extra dimensions, if they exist, are compactified at the Planck scale, about 10 to the minus 35 meters. That's unimaginably small, 20 orders of magnitude smaller than a proton. At the scales we experience, even at the scales we can probe with our most powerful instruments, space appears smooth and 3-dimensional. Only at the Planck scale would the curled up extra dimensions become apparent. It's a bit like looking at a sheet of paper. From far away, it looks 2-dimensional, just a flat surface. Get closer, and you might notice it has thickness, a 3rd dimension. Get even closer with a microscope, and you see the paper fibers' 3-dimensional structures. Zoom in further with an electron microscope, and you see molecules, atoms, particles, each adding complexity and structure invisible from farther away. The extra dimensions of string theory are like that, present at every point in space, but only detectable at scales we haven't yet learned to probe. Hidden dimensions aren't really hidden. They're just small, operating at scales beyond our current reach. So string theory gives us a universe with hidden dimensions. Brain cosmology gives us a framework where our universe is a 3-dimensional membrane in a higher dimensional bulk. And together, they suggest that black holes might be higher dimensional structures, potentially connecting different regions of the bulk, possibly even creating pocket universes within themselves. This sets the stage for one of the most audacious ideas in modern cosmology, that our universe, the entire observable cosmos, might be the interior of a black hole in a higher dimensional space. That what we call the Big Bang might have been the formation of an event horizon viewed from inside. That we're not just observing black holes from outside, but living inside one, experiencing its interior as our entire reality. It sounds insane, but once you understand the framework of extra dimensions of brains floating in the bulk of higher dimensional black holes, it becomes not just possible, but almost natural, a logical extension of the mathematics. Let's take a breath here. Let these ideas settle. Extra dimensions curled at impossible scales. Brains floating in bulk space. Black holes as multidimensional structures. It's a lot to hold in your mind at once. Now, we come to the hypothesis itself, the idea that's been lurking at the edges of our discussion. Since the beginning, our universe is inside a black hole. Let's be precise about what this means. The proposal is that in a higher dimensional space, a parent universe with perhaps 4 or 5 spatial dimensions instead of 3, there existed matter and stars and gravity, just like in our universe, but with more dimensions. At some point, a sufficiently massive object in that parent universe collapsed under its own gravity, forming a black hole according to the physics of that higher dimensional space. From the perspective of observers in that parent universe, they see a black hole. It has an event horizon, a boundary beyond which nothing can escape. It has a singularity at its center where space-time curvature becomes extreme. It behaves according to all the rules we've discussed, just generalized to more dimensions. But inside that black hole, conditions were such that the collapsing matter didn't simply crash into a singularity and stop. Instead, the extreme curvature of space-time, the warping of dimensions, created a kind of bubble, a pocket of space that began expanding according to its own dynamics. That bubble is our universe. The moment of the black hole's formation, viewed from outside, corresponds to what we call the Big Bang, viewed from inside. The event horizon of that higher dimensional black hole is from our interior perspective, the cosmic horizon, the observational boundary beyond which we cannot see. Time dilation, due to the extreme gravity, means that while relatively little time has passed in the parent universe, since the black hole formed, billions of years have elapsed inside, giving rise to galaxies, stars, planets, and eventually life. It's like when you realize you're part of something much larger than yourself. The feeling of being small, but also connected. This hypothesis draws on something called the holographic principle, one of the most profound insights to emerge from studying black holes. The holographic principle states that all the information contained within a volume of space can be encoded on the boundary of that volume on a surface one dimension lower. It's called holographic because it's similar to how a two-dimensional hologram can encode a three-dimensional image. The principle emerged from studying black hole thermodynamics. Physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of disorder or information, is proportional not to its volume, but to the surface area of its event horizon. This was shocking because entropy usually scales with volume. If you double the size of a box of gas, you double its entropy. But for black holes, if you double the radius, you quadruple the surface area. And that's what determines the entropy. Leonard Susskind and Gerard 't Hooft developed this insight into the holographic principle. They proposed that the event horizon of a black hole is fundamentally two-dimensional, and all the information about what's inside is encoded on that two-dimensional surface. The three-dimensional interior is in some sense a projection from the information on the boundary. If this applies to black holes, might it apply to the universe as a whole? Could our three-dimensional universe, with all its complexity, all its history, all its information be encoded on a two-dimensional boundary. If we're inside a black hole, that boundary would be the event horizon. Everything we experience, every particle, every field, every interaction, might be a kind of holographic projection from information encoded on a distant two-dimensional surface we can never reach. This sounds like we're living in a simulation, and in a sense, that's not far off. The holographic principle suggests that our experience of three-dimensional space might not be fundamental, but emergent, arising from more basic two-dimensional information. It's not that we're in a computer simulation, but rather that the universe's information structure might work in a way more similar to computation than we previously imagined. Now let's connect this to cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, growing by a factor of at least 10 to the 26, doubling in size every 10 to the minus 37 seconds. This expansion was far faster than light, which sounds like it violates relativity, but it doesn't, because space itself was expanding, not objects moving through space. Inflation solves several problems in cosmology. It explains why the universe is so uniform, why the cosmic microwave background has the same temperature in all directions. It explains why space appears flat rather than curved. But what caused inflation? What drove that exponential expansion? Here's a possibility. If our universe formed inside a black hole in a higher dimension, the expansion of our universe's event horizon, viewed from outside, might correspond to inflation viewed from inside. As the black hole in the parent universe swallows matter and energy, its event horizon grows. From inside, this growth manifests as rapid expansion of space. What we call inflation might simply be the interior experience of a black hole's event horizon, expanding as it forms and accretes initial matter. This is pretty wild. We're saying we live in a cosmic box, but it's a universe-sized box, so roomy. The hypothesis also provides a natural explanation for why the Big Bang happened everywhere at once. If you think of the Big Bang as an explosion at a point, you run into problems. What was at the center? What direction did it explode? But if the Big Bang was the formation of an event horizon, then it didn't happen at a point. An event horizon is a surface, and from inside it surrounds everything. The Big Bang would have been the simultaneous formation of all of space, not an explosion expanding into pre-existing space. Why doesn't this idea contradict observations? If we're inside a black hole, shouldn't things look different? Not necessarily. From inside the event horizon, space and time are so warped that all the normal rules still apply locally. Light still travels at light speed. Gravity still works according to Einstein's equations. Stars form planets, orbit life, evolves. The only difference is the large-scale structure, the topology of space-time itself. Moreover, we can't see beyond the cosmic horizon, the observational boundary of our universe. Light from beyond that distance hasn't had time to reach us. If that cosmic horizon is actually the event horizon of the black hole we're inside, we'd never know the difference. We can't see past an event horizon from inside any more than we can from outside. The similarities between our universe and the interior of a black hole are striking. Both have a boundary we cannot cross or see beyond. Both have time flowing in only one direction. Both have curved space-time. Both expand from an initial state of extreme density. Both have a horizon that, once crossed, defines a region causally disconnected from what's outside. I know this story is getting strange, but stay with me. The strangeness is where the truth might hide. Critics of this hypothesis point out real problems, of course. Our universe doesn't have an obvious center, the way we'd expect inside a black hole, with a central singularity. The universe appears homogeneous and isotropic, the same in all directions, which seems inconsistent with the interior of a black hole. And we don't observe the kind of extreme tidal forces near our cosmic horizon that we'd expect near an event horizon. But proponents counter that these objections assume a black hole interior must look like what simple models predict. If the black hole is rotating, if it's supermassive enough, if it exists in higher dimensions, with different geometry, the interior might look very different from naive expectations. The math allows for pocket universes inside black holes that don't have these problems, that could appear homogeneous and expanding just like our universe does. The black hole universe hypothesis also connects to theories of eternal inflation and the multiverse. If black holes can give birth to universes, and those universes contain black holes, which give birth to universes of their own, you get an infinite fractal structure. Universes within universes within universes, branching eternally. Each black hole becomes a seed for a new cosmos. Each universe is both parent and child, containing offspring universes in its black holes, while itself being contained in a black hole in its parent universe. In this view, our universe isn't special or unique. It's one bubble in an infinite foam, and that actually makes a kind of sense. Why should existence be limited to what we can see? If physical laws allow for universe creation through black hole formation, and black holes are common, then universes should be common too. The multiverse becomes not just possible, but inevitable. Does this mean the Big Bang wasn't unique? That universes are constantly being born inside black holes? That creation isn't a one-time event, but an ongoing process scattered throughout the multiverse? Yes, that's exactly what it means. And if you find that thought dizzying, overwhelming, even terrifying, you're not alone. It removes Earth from the center of everything, removes humanity from any special place, removes even our entire universe from uniqueness. We become one instance of a pattern that repeats infinitely. But there's beauty in that too. It means we're part of something incomprehensibly vast, an eternal dance of creation and destruction, universes within universes forever. This hypothesis remains speculative, controversial, far from proven, but it's not crazy. It emerges naturally from well-established physics, general relativity, quantum mechanics, thermodynamics. It solves conceptual problems about the Big Bang and inflation. It connects to cutting-edge ideas in string theory and brain cosmology. And it offers a grand unified picture where black holes aren't endpoints, but gateways, where destruction and creation are two sides of the same cosmic process. Whether or not we're inside a black hole, thinking about the possibility expands our sense of what reality might be. It challenges us to imagine existence beyond the boundaries of what we can observe. It asks us to consider that what seems like everything might be just a tiny part of an infinite whole. And that's where we'll go next, deeper into the multiverse, into theories of parallel universes, alternate realities, and the possibility that black holes are bridges between them. But first, let that image settle. Our universe as the interior of a black hole, creation as an ongoing process, existence as nested dolls universes within universes forever. Hold that thought as we continue. If our universe can exist inside a black hole, what about other universes? Could every black hole contain an entire cosmos? And if so, how many universes might there be? Welcome to the multiverse, one of the most mind-expanding ideas in modern physics. The multiverse hypothesis suggests that our universe isn't alone. There are countless others, perhaps infinitely many each, with its own space-time laws of physics and history. And black holes might be the bridges connecting them. The bubble universe model is one way to visualize this. Imagine the multiverse as an infinite ocean of higher dimensional space, and each universe is a bubble floating in that ocean. Each bubble has its own interior geometry, its own 3 dimensions of space, its own time. The bubbles are causally disconnected, meaning nothing inside one bubble can affect or communicate with what's inside another. They're completely separate realities. In eternal inflation theory, these bubble universes form constantly. The process of inflation, that exponential expansion in the early universe, never truly ends everywhere. In most regions, inflation continues forever, but occasionally a bubble nucleates, where inflation stops, and a universe with stable laws of physics forms. That's our universe. But elsewhere in the inflating sea, other bubbles are constantly forming, each one a new universe, with potentially different physical constants, different numbers of dimensions, different particles and forces. Now add black holes to this picture. If our universe formed inside a black hole from a parent universe and our universe contains black holes, then each of those black holes might give birth to a child universe of its own. It's a fractal structure, endlessly nested. The parent universe has black holes that create universes which have black holes, that create universes which have black holes on and on without end. Every choice you make might create a branch, a personal multiverse of possibilities. In cosmic terms, every black hole might be doing the same. This is the concept of baby universes. When a black hole forms in our universe, conditions at the singularity might be so extreme that instead of just crushing matter into infinite density, space-time itself buds off, creating a new region of space-time, connected to ours only through the black hole. From our perspective, matter falls into the black hole and disappears. From the perspective of the baby universe, that infalling matter becomes the energy and mass of a new cosmos, igniting its own Big Bang. The baby universe would have no way to communicate back to us. The event horizon is a one-way barrier. Information can fall in, but never escape out. So each baby universe is born, evolves, perhaps creates its own black holes and baby universes, and we never know. It's completely isolated from us existing in its own bubble of space-time. But here's where it gets stranger. If black holes create new universes, could there be exits as well as entrances? Could the opposite of a black hole exist? Theoretically, yes. They are called white holes. A white hole is a time-reversed black hole. Where a black hole has an event horizon, you can enter but never leave. A white hole has a horizon. You can leave but never enter. Where a black hole pulls everything inward, a white hole expels everything outward. Matter and light and energy burst out of a white hole, but nothing from outside can ever reach it. White holes are mathematically valid solutions to Einstein's equations, just as black holes are. But we've never observed one, and there are good reasons to think they probably don't exist in our universe, at least not for long. They'd be incredibly unstable, and the process that creates black holes, gravitational collapse, doesn't have an obvious, time-reversed equivalent that would create white holes. But in the context of the multiverse, white holes become interesting again. What if a black hole in our universe connects to a white hole in another universe? Matter falls into the black hole here, travels through some kind of connection, and emerges from a white hole there. The black hole would be like a drain, and the white hole like a fountain, connected by a pipe that runs through higher dimensional space, or through the structure of space-time itself. This brings us to wormholes, theoretical tunnels through space-time that connect distant regions or even separate universes. Einstein and Nathan Rosen discovered wormhole solutions to relativity back in 1935. The Einstein-Rosen bridge, as it's technically called, connects two black holes through a throat in spacetime. The problem is that these wormholes are unstable. They collapse almost instantly, faster than light could traverse them. To keep a wormhole open long enough for anything to pass through, you'd need what physicists call exotic matter, matter with negative energy density. This isn't the same as antimatter. It's something even stranger matter that violates the usual energy conditions. We've never seen exotic matter in nature, though some quantum effects produce something vaguely similar on microscopic scales. But imagine if a sufficiently advanced civilization or some natural cosmic process could stabilize a wormhole. Or imagine if the connection between a black hole and its baby universe creates a natural wormhole-like structure. Then black holes become portals, gateways linking different regions of the multiverse. Black holes are like doors in an infinite house. Each door leads to a different room, a different universe. Even without physical connections, black holes might link universes through quantum entanglement. Entanglement is the phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein called it spooky action at a distance, and never liked it, but it's been confirmed by countless experiments. Some physicists have proposed that entanglement and space-time geometry are deeply connected. That entanglement might be what holds space-time together at a fundamental level. If that's true, then entangled particles falling into different black holes, or into a black hole in one universe and remaining outside in another, could create quantum correlations between universes. Information wouldn't pass between them in any classical sense, but the universes would be linked through the quantum fabric of reality. This gets into speculative territory, blending quantum mechanics, general relativity, and information theory in ways we don't fully understand yet. But the basic idea is that black holes might create quantum bridges between universes entangling their fundamental structures, even if matter and energy can't flow between them. There's also the question of why each black hole should create a different universe. Couldn't they all lead to the same place? In principle, yes. But the conditions at each black hole's singularity would be different. The mass, spin charge, and quantum state of each black hole would impart different initial conditions to its baby universe. So each one would create a cosmos with potentially different laws, different constants, different history. Some might be similar to ours, differing only in minor details. Others might be radically alien, with different numbers of dimensions, different particles, physics we couldn't recognize. The multiverse of black hole baby universes would be vastly diverse, an infinite sampling of possible realities. Thankfully, we don't need passports to travel between universes, though it would make for interesting customs declarations. If this picture is correct, then our universe isn't isolated. We're part of an incomprehensibly vast web of connected realities. Every black hole is a door, and behind every door is another cosmos, as real and complex as our own. Some of those universes might contain black holes that connect to still other universes, creating layers upon layers, an infinite fractal of existence. And somewhere in that fractal, in some baby universe, born from a black hole in a universe, we'll never see beings might be looking up at their sky, wondering if they're alone, asking the same questions we're asking, never knowing that they're our cosmic descendants, children of our black holes, inheritors of structure and information that cascaded down from our universe to theirs. The multiverse isn't just about quantity, though. It's about possibility. If baby universes exist, then reality is experimenting, trying out every possible combination of laws and constants and initial conditions. Somewhere in the multiverse, every possibility that can exist does exist. The imagination of physics becomes reality somewhere. And here, we are one possibility among infinite others, looking out and wondering what else is there. Let's ground ourselves for a moment. We've been drifting through abstractions, infinite universes, quantum connections. Let's return to something more concrete, the mathematics that makes all this possible. All these ideas about black holes, universes within universes, higher dimensions, they're not just wild speculation. They're rooted in mathematics, in equations that describe how reality behaves. So how do scientists actually work with these concepts? How do they test ideas about things they can't directly observe? The foundation is Einstein's field, equations the core of general relativity. These 10 interlinked differential equations relate the curvature of spacetime to the distribution of mass and energy. They're notoriously difficult to solve. Einstein himself could only solve them for very simple cases, but these equations are what predict black holes, gravitational waves, the expanding universe, all the large-scale structure of spacetime. Carl Schwarzschild found the first exact solution in 1916 describing a non-rotating uncharged black hole. His solution gave us the Schwarzschild radius, the size of the event horizon for a given mass. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's about 9 millimeters. These numbers tell us how much we'd have to compress these objects to turn them into black holes. In 1963, Roy Kerr found another exact solution describing rotating black holes. The Kerr solution is more complicated than Schwarzschild's because rotation adds angular momentum and frame dragging effects. But it's also more realistic because most black holes in nature probably rotate formed from rotating stars that conserved their angular momentum as they collapsed. These analytical solutions are beautiful and exact, but they only work for idealized, isolated black holes. Real black holes interact with their surroundings, merge with other black holes, accrete matter, and live in dynamic environments. To understand these situations, you can't solve the equations by hand. You need computers. It's like planning your future. You simulate what hasn't happened yet, running possibilities through your mind to see what might work. This is where numerical relativity comes in. Scientists break space-time into a lattice of points, and calculate how the curvature at each point evolves based on the matter and energy nearby. It's like creating a three-dimensional spreadsheet where each cell contains information about space-time curvature, and you update every cell based on its neighbors and Einstein's equations. The computational challenge is enormous. Einstein's equations are nonlinear, meaning small changes can cascade into big effects. They're also highly coupled, meaning what happens at one point depends on what's happening everywhere else. And you need incredible precision because you're tracking things like gravitational waves, tiny ripples in space-time that require detecting changes smaller than an atomic nucleus over distances of kilometers. Supercomputers run these simulations, breaking the problem across thousands of processors working in parallel. They might spend weeks of real time simulating 1 second of a black hole merger. The amount of computation required is staggering, but the results have been worth it. Computers spend weeks simulating 1 second of a black hole's life. Talk about patience. When LIGO detected gravitational waves from merging black holes in 2015, scientists already knew what the signal should look like because they'd run countless simulations. They'd modeled black holes of different masses, spiraling together, merging, ringing down into a single larger black hole. They'd cataloged the gravitational wave signatures each scenario would produce. So when the actual waves arrived at LIGO's detectors, they could match the signal to their library of simulations and say, this is two black holes, 29 and 36 solar masses merging together 1.3 billion light years away. That's the power of numerical relativity. It lets us predict phenomena we can't directly observe and then recognize them when we detect their effects. But why does mathematics work so well at predicting physical reality? Why should equations written on paper describe black holes across the universe? This is one of the deep mysteries of physics. Mathematics is a human invention, a language we created to describe patterns. Yet it predicts aspects of nature we've never observed in conditions far beyond human experience. Einstein's equations predicted black holes before we found them. They predicted gravitational waves decades before we detected them. They predict the bending of light around massive objects, the slowing of time in gravitational fields, the expansion of the universe, all confirmed by later observation. How does mathematics know what reality will do? The answer might be that mathematics isn't describing reality directly. It's describing the logical structure that reality must follow. The universe operates according to consistent rules, and mathematics is the language of consistency, of logical necessity. If space and time are real, and if energy and momentum are conserved, then Einstein's equations follow almost inevitably. The math isn't magic. It's the working out of implications. Simulations also help us understand black hole interiors, even though we can't observe them directly. By evolving Einstein's equations, forward in time for matter falling into a black hole. Scientists can calculate what happens past the event horizon. The singularity remains problematic because the equations break down there, returning infinities. But numerical simulations suggest various possibilities, maybe singularities, are hidden behind event horizons safely censored from the outside universe. Maybe quantum effects prevent true singularities from forming. Maybe space-time has some graininess at the smallest scales that prevents infinite curvature. These simulations also explore scenarios like black holes in higher dimensions relevant to string theory and brain cosmology. A 5-dimensional black hole behaves differently from a 4-dimensional one. The event horizon has a different shape. The gravitational waves it produces have different frequencies. By simulating these scenarios, scientists can predict what we should observe if extra dimensions exist and if black holes extend into them. Computational cosmology goes further, simulating the evolution of entire universes. Start with initial conditions, matching what we observe. In the early universe, apply the laws of physics and watch how structure forms over billions of simulated years. Do galaxies form the way we see them? Do supermassive black holes grow at the centers? Does the distribution of matter match observations? These simulations confirm that our understanding of physics is on the right track. The simulated universes look remarkably like the real one, suggesting we've captured something essential about how reality works. And they let us explore counterfactuals. What if dark energy was stronger? What if the initial density fluctuations were larger? What if physical constants had different values? We can run these universes and see what happens. In the context of the multiverse, these simulations hint at how different universes might look. Each baby universe born from a black hole would have slightly different initial conditions. Running simulations with varied parameters shows us the range of possible outcomes, from universes that expand forever to those that recollapse quickly, from universes teeming with structure to those that remain nearly uniform. Mathematics and computation have become our telescopes for exploring spaces we cannot physically reach, times we cannot visit, scales we cannot measure. They extend our vision beyond the limits of observation into the hearts of black holes across the multiverse through higher dimensions. And they all point toward stranger realities than we ever imagined. But there's still one place we haven't fully explored: the interior of the event horizon itself. What happens when you cross that boundary? What waits at the center? Let's take that final journey inward. We've talked about event horizons from the outside, seen them in photographs, discussed them in theory. But what actually happens if you fall in? What do you experience as you cross that boundary and plunge toward the singularity? Let's start with what you'd feel. Surprisingly, for a supermassive black hole, like the ones at galactic centers, you'd feel nothing special as you crossed the event horizon. No barrier, no flash of light, no sensation of passing through anything. From your perspective, space looks normal, time flows normally, and you continue falling inward, pulled by gravity, just as you were before crossing. The event horizon is a point of no return, but it's not a physical thing. It's a mathematical surface, a place where the geometry of space-time changes in a crucial way. Inside it, every direction you could travel leads deeper inward. There's no outward anymore. The singularity at the center becomes part of your inevitable future, as certain as tomorrow, because all paths through spacetime lead there. It's like crossing a point of no return in life. Once past it, there's only forward, never back. Outside the black hole, an observer watching you would see something different. As you approach the event horizon, you'd appear to slow down from their perspective. Time dilation would stretch your seconds into their hours, then days, then years. You'd appear to freeze at the horizon, your image red shifting into invisibility as the light waves from you became infinitely stretched. To them, you'd be frozen forever, at the boundary never quite crossing, even though infinite time passes. But you cross immediately from your own perspective, experiencing no delay. This is the strange duality of black holes. What happens depends on where you're watching from. Once inside, time and space swap roles in a sense that's difficult to grasp intuitively. Outside the event horizon, you can move forward or backward in space, but only forward in time. Inside, the singularity isn't a place in space you could avoid by going a different direction. It's a moment in time in your inevitable future. Moving forward through time brings you closer to the singularity, just as moving forward through time outside brings you closer to tomorrow. You can no more avoid the singularity than you can avoid the next second. This temporal nature of the interior is why nothing escapes. It's not that the gravity is too strong to overcome, though it is. It's that escape would require traveling backward in time, which is impossible. As you fall inward, spaghettification becomes a concern. For stellar mass black holes, the tidal forces would tear you apart long before you reached the horizon. Your feet, closer to the singularity, experience stronger gravity than your head. The difference stretches you like taffy, pulling you longer and thinner until molecular bonds break, then atomic bonds, until you're reduced to a stream of particles spiraling in. But for supermassive black holes, the event horizon is so far from the center that tidal forces there are gentle. You could cross intact, surviving hours or even days inside before tidal forces grew strong enough to destroy you. In those final moments, you'd see strange things. Light from outside the black hole would blue shift, becoming more energetic, potentially creating a brilliant ring around your view of the outside universe. Time dilation would mean you'd see the external universe evolving rapidly, stars dying, galaxies colliding, eons passing in what seems like minutes to you. At the center waits the singularity, a point where space-time curvature becomes infinite and our physics breaks down completely. General relativity predicts it, but general relativity is also a classical theory, not accounting for quantum mechanics. Most physicists suspect that quantum effects become important at extreme scales, preventing true infinity. One alternative is the Planck star, proposed by loop quantum gravity. Instead of infinite density, matter compresses to the Planck density about 10 to the 93 grams per cubic centimeter, incomprehensibly dense but finite. At this density, quantum gravitational effects create a bounce and outward pressure that might halt the collapse. The singularity becomes a ultra-dense core, incredibly small, but not a point, not infinite. If Planck stars exist, What you'd encounter at the center isn't an end, but a transformation. Perhaps the bounce creates a white hole, expelling matter into another universe. Perhaps it creates a baby universe inside the black hole, branching off into its own space-time. You'd be torn apart by tidal forces long before reaching it. But the matter and energy you contribute would seed that new cosmos. The singularity might be like the end of one story and the beginning of another. Not an ending, but a transition. There's also the black hole information paradox to consider. According to quantum mechanics, information cannot be destroyed. Every particle, every interaction carries information about its history, and that information is preserved in the quantum state of the universe. But when something falls into a black hole and reaches the singularity, where does its information go? Hawking radiation complicates this. Black holes slowly evaporate, emitting radiation due to quantum effects near the event horizon. Over immense timescales, a black hole could evaporate completely. If the information that fell in is destroyed, quantum mechanics is violated. If it's preserved but trapped in the singularity, it's still lost. When the black hole evaporates, if it somehow escapes in the Hawking radiation, we need to understand how information gets from the singularity back out past the event horizon, which seems impossible. This paradox remains unresolved, one of the deepest problems in theoretical physics. It suggests that our understanding of black holes, quantum mechanics, or both is incomplete. Solving it might require a theory of quantum gravity that unifies general relativity and quantum mechanics, showing how information behaves in extreme curvature. Some proposals suggest information is encoded on the event horizon itself, in accordance with the holographic principle. Everything that falls in leaves an imprint on the horizon's quantum structure. When the black hole evaporates, that information is released back into the universe through subtle correlations in the Hawking radiation. The information isn't lost, just scrambled in ways that are extraordinarily difficult to decode. Why can't we see the singularity from outside? Because of cosmic censorship, a principle suggested by Roger Penrose. Nature seems to hide singularities behind event horizons, preventing them from being visible to the outside universe. This is fortunate, because a naked singularity one without an event horizon would be a place where the laws of physics simply don't apply, a point from which anything could emerge without cause or explanation. Event horizons protect the rest of the universe from this chaos. Falling into a black hole would be the ultimate one-way journey. You'd experience time dilation, watch the universe age. Around you feel space itself curve toward an inevitable end. In those final moments, before tidal forces tore you apart, you might wonder if your atoms would become part of a new universe, if the singularity you're falling toward is the Big Bang of another cosmos. You'd never know the answer, but the universe, in its strange way, might be answering on your behalf, recycling your matter and energy into new forms, new structures, perhaps even new realities. Imagine drifting gently through curved space, time slowing around you like honey, all worries dissolving into the dark. The singularity ahead isn't frightening, but peaceful, a place where all questions end and something new begins. You float there suspended, the boundaries between inside and outside fading away. The universe itself becomes a soft, welcoming, pulling you into rest. Your eyes close naturally easily, and you drift into the quiet dark where time no longer means anything, and you can finally fully rest. Sleep well. Tomorrow we'll explore what all this means for reality consciousness and existence itself. But for now, let go. Just let go and float. We've journeyed through black holes, explored universes within universes, contemplated hidden dimensions. But here's a humbling truth. We only understand about 5% of the universe. The other 95%, complete mystery. This is where dark matter and dark energy enter the story. Two invisible components that dominate the cosmos, yet remain frustratingly beyond our grasp, and they might connect to black holes in unexpected ways. Dark matter was discovered in the 1930s when Fritz Zwicky noticed galaxies in clusters moving too fast. There wasn't enough visible matter to hold them together. They should have flown apart, yet there they were, stable and bound. Zwicky concluded invisible matter must be providing additional gravity. Later observations confirmed this. Stars at the edges of galaxies orbit just as fast as those near the center, which makes no sense based on visible matter alone. There must be vast halos of dark matter surrounding each galaxy, providing the extra gravitational pull. Dark matter makes up 27% of the universe. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. We only know it exists because of gravity. It's invisible scaffolding, holding galaxies together. But what is it? Maybe WIMPs, weakly interacting, massive particles. Maybe axions, ultralight particles acting like waves. Maybe sterile neutrinos, interacting only through gravity. Experiments worldwide search for these particles in underground detectors, but so far, nothing. 95% of the universe is invisible, like an iceberg, where we only see the tip, or like everything about yourself you haven't yet discovered. Here's the connection to black holes. Some scientists propose dark matter might be primordial. Black holes, tiny black holes, formed moments after the Big Bang from density fluctuations. If they exist in the right abundance, they could account for dark matter. They'd have mass, provide gravity, emit no light, and be nearly impossible to detect. Unlike hypothetical particles, we know black holes exist. Then there's dark energy, even stranger. In the late 90s, astronomers discovered the universe's expansion is accelerating. Galaxies aren't just moving apart, they're moving apart faster. Something is pushing them, driving space itself to expand at increasing rates. That something is dark energy, making up 68% of the universe. Unlike dark matter, which clumps dark energy, spreads uniformly, it acts like repulsive force, pushing everything apart. The more space exists, the more dark energy exists, creating more space in an accelerating cycle. What causes it? Nobody knows. It might be a property of space itself, energy from quantum vacuum fluctuations, or something entirely new. We confidently named them dark because, well, we literally can't see anything. At least we're honest. Here's where it connects to the black hole universe hypothesis. If we're inside a black hole, in higher dimensional space, dark energy might result from interactions with the parent universe. The expansion we observe might be driven by forces outside our cosmic boundary, pushing on the event horizon containing us. Similarly, dark matter around galaxies might hint at higher dimensional structure. If black holes are multidimensional objects intersecting our universe, dark matter could be gravitational effects from matter in dimensions we can't see. These ideas push beyond confirmed science into speculation, but they show how the universe's biggest mysteries might connect to black holes and hidden dimensions. Let's shift focus now from what's invisible to something stranger, the possibility that everything we experience might not be as real as we think. The holographic principle is one of the most unsettling ideas from black hole physics. It suggests our three-dimensional reality might be an illusion, that true information is encoded on a two-dimensional surface, and everything we perceive is projection. This sounds like science fiction, like we're in a simulation. But the holographic principle comes from rigorous physics, from studying information near black holes. Jacob Bekenstein discovered in the 70s that black hole entropy scales with surface area, not volume. For ordinary objects, entropy scales with volume. A box twice as large has twice the entropy, but for black holes, it's surface area that matters. This suggested all information about what's inside is somehow encoded on the two-dimensional event horizon. Gerard 't Hooft and Leonard Susskind developed this into the holographic principle in the 90s. They proposed this isn't just true for black holes, but for any space region. Maximum information in a volume is proportional to its boundary area, not volume itself. The universe might be a hologram where three-dimensional images emerge from two-dimensional information. Have you ever felt life is a projection of something deeper you can't quite see? Maybe you're sensing what physics describes. Think of an actual hologram on a credit card. It's flat two-dimensional, but when light hits it right, a three-dimensional image appears. The 3D image isn't really there. It's an illusion created by patterns on the flat surface. Yet it looks and behaves like it has depth. Reality might work similarly. The deepest description, fundamental information, might be encoded on a two-dimensional surface. The three-dimensional universe we experience emerges from that encoding, a projection appearing real, but built from lower dimensional information. Like photos on your phone, two-dimensional images containing your entire three-dimensional memories, capturing depth and space in flat pixels. Juan Maldacena's ADIS CFT correspondence in '97 provided mathematical proof. It showed a gravity theory in higher dimensional space exactly equals a no-gravity theory on that space's boundary, a concrete realization of holography. If our universe operates holographically, where's the encoding surface? If we're inside a black hole, it's the event horizon surrounding us, the cosmic boundary we can never reach. Everything in our three-dimensional universe might be fully described by information encoded on that distant two-dimensional surface. This raises profound questions. If we're projections from a boundary, what about consciousness, free will existence itself? Are we truly three-dimensional beings, or patterns of information on a surface experiencing themselves as three-dimensional? If this story were a hologram, the central idea was encoded from the start. Everything after is projection and elaboration. The holographic principle doesn't mean reality is fake. It means reality is structured differently than intuition suggests. Three-dimensional space might be emergent, arising from two-dimensional information, but it's no less real. Water emerges from molecules, but is genuinely wet. Space might emerge from holographic encoding, but is genuinely spatial. This might resolve the information paradox. If information is stored on the event horizon rather than inside when black holes evaporate, information escapes because it was always on the surface. Testing this is extraordinarily difficult, but indirect evidence comes from mathematics working consistently, from ADS-CFT holding up, from the principle solving paradoxes and connecting physics areas unexpectedly. If we live holographically, it doesn't change daily experience. You exist. Your thoughts are real. Relationships matter. The difference is only in how deeply we understand the structure underneath. Now let's turn to the people who discovered these ideas, who argued about them, refined them, sometimes changed their minds completely. Behind every equation, every theory, every breakthrough are people. Human beings who argue, doubt, get it wrong, occasionally admit mistakes. The black hole story is also about remarkable individuals whose conversations shaped understanding. John Wheeler coined black hole and explored wild ideas. He proposed reality emerges from information captured in it from bit, suggesting physical existence arises from binary choices. Wheeler saw information as more fundamental than matter, anticipating holography by decades. Leonard Susskind, loud and brilliant, developed the holographic principle and fought for information preservation. He engaged in decades-long debate with Stephen Hawking over whether information is destroyed in black holes. Susskind insisted it must be preserved. He was right. Gerard 't Hooft approached holography differently, but reached similar conclusions. His work emphasized mathematical structure, showing rigorously how boundary information describes bulk physics. Stephen Hawking discovered black holes emit radiation and evaporate. This created the information paradox. Hawking initially believed information was destroyed, violating quantum mechanics. He and Susskind argued for years, Hawking even betting information is lost. Hawking and Susskind argued for years. Then Hawking admitted he was wrong. That's true. Greatness changing your mind when evidence demands it. In 2004, Hawking conceded. He'd been wrong. Information is preserved. This exemplified scientific integrity. Already legendary, Hawking admitted error, publicly updating views based on new arguments. Like when you change thinking based on new evidence. That's growth in science and life. Roger Penrose contributed cosmic censorship, the idea nature hides singularities behind horizons. His work with Hawking proved singularities are inevitable in black holes and Big Bang. Alan Guth developed inflation theory, explaining exponential early expansion. While not directly proposing black hole universe hypothesis, his model connects naturally to the idea. Lee Smolin proposed cosmological natural selection. Black holes create baby universes with varying constants. Universes producing more black holes generate more offspring, creating evolutionary pressure toward black hole-friendly universes. Nikodem Poplavsky worked out detailed black hole universe models using Einstein-Cartan theory, showing torsion might prevent singularities, creating bounces, spawning new universes. These debates matter because science advances through argument. Wheeler imagined wildly. Hawking calculated carefully. Suskind fought tenaciously. Hooft reasoned rigorously. Together, through agreement and disagreement, they pushed understanding forward. Science isn't just equations. It's people struggling with mystery, changing minds when wrong, celebrating when right. The humanity behind the physics makes it real, and their debates continue. The information paradox isn't fully solved. The holographic principle isn't completely proven. The black hole universe hypothesis remains speculative, but that's how science works. Provisional answers, ongoing questions, eternal curiosity, driving us forward into the unknown. The black hole universe hypothesis is fascinating, elegant, and connects many ideas beautifully. But it faces serious challenges, real problems that prevent scientists from accepting it as established fact. Let's be honest about what we don't know and why this remains speculation rather than confirmation. The first major problem: we don't observe an event horizon surrounding our universe. If we're inside a black hole, there should be a boundary. We can detect some signature of the event horizon enclosing us. Instead, space appears to extend uniformly in all directions. The cosmic horizon we observe is simply the limit of how far light has traveled in 13.8 billion years. It looks nothing like the dramatic warping boundary of a black hole's event horizon viewed from outside. Proponents argue the event horizon would be invisible from inside, that we'd never perceive it directly. But critics counter that there should be observable effects, subtle signatures in the cosmic microwave background, or in the distribution of galaxies that hint at this boundary. So far, nothing. Second challenge: gravity inside our universe doesn't match expectations for black hole interiors. Near a black hole's event horizon, gravitational effects should be extreme. Tidal forces, time dilation, space-time curvature should all be dramatic. Yet our universe appears relatively gentle gravitationally. Time flows uniformly everywhere we can measure. Space curves smoothly on large scales, but not catastrophically. For supermassive black holes, proponents argue the interior can be surprisingly gentle because the event horizon is so far from the center. The tidal forces aren't extreme until you get much closer to the singularity. Maybe our position inside gives us a misleadingly calm view, but this requires specific conditions, special circumstances, making the hypothesis less general and more contrived. It's like a hypothesis in your own life. Makes sense, feels right, but you can't quite prove it yet. Third problem: our universe is homogeneous and isotropic, meaning it looks the same in all directions with no preferred center. But black hole interiors should have structure. There should be a center where the singularity sits, and space should be organized around that point. Everything should be falling toward it. Yet when we look at the universe, we see no center, no preferred direction, no cosmic down toward a singularity. The universe appears uniform. This is perhaps the strongest objection. How can we be inside a black hole if there's no singularity defining a center? Proponents suggest rotating black holes or higher dimensional geometries might avoid this problem, creating interiors that appear homogeneous from within. But this requires increasingly complex models with increasingly specific conditions. Fourth, we don't observe a central singularity. In a typical black hole, there's a point at the center where density becomes infinite. All matter inside is inevitably drawn toward it. Yet our universe has no such point. There's no location that serves as the ultimate destination for all matter, no place where everything is falling. Some models propose the singularity is in our past rather than our future, that the Big Bang itself was the singularity we emerged from rather than one we're falling toward. But this inverts the usual black hole picture in ways that strain the analogy. Science says, interesting idea, but show me the proof. Fifth challenge. Expansion rates don't match predictions. Our universe is expanding, and that expansion is accelerating. But if we're inside a black hole, the expansion should relate to the black hole's event horizon, growing as it accretes matter. The rates don't seem to align. Our universe's acceleration, driven by dark energy, doesn't obviously correspond to what we'd expect from infalling matter, increasing a black hole's size. Then there's the scale paradox. Our observable universe contains billions of galaxies each, with billions of stars. The total mass is incomprehensibly vast. If all this is inside a black hole, that black hole must be enormous, far larger than any we've observed. Where are these super colossal black holes? If every universe is inside one, and universes are common in the multiverse, we should see evidence of universe-scale black holes in the parent universe. But we don't because we can't see outside our own universe to check. What would it take to confirm this hypothesis? We'd need to detect signatures of the event horizon, enclosing us, measure effects from higher dimensions, observe connections between our universe and a parent cosmos, or find some test that distinguishes inside a black hole from not inside a black hole. So far, no such test exists. It's a beautiful painting missing a few crucial pieces, leaving the full picture incomplete. The hypothesis remains intriguing because it's not obviously wrong, just unproven. It connects ideas elegantly, offers explanations for cosmic inflation, and the Big Bang fits with multiverse theories and higher dimensions. But elegance isn't evidence. Beauty isn't proof. Science requires testable predictions and observational confirmation. So we're left in an interesting place, a hypothesis that's plausible, creative, mathematically consistent, yet possibly unprovable with current or even foreseeable technology. It might be true, it might be false, or it might be one of those questions that lies forever beyond the reach of observation, tantalizing but unanswerable. And maybe that's okay. Maybe not every question has an answer we can access. Maybe some mysteries remain mysterious, not because we're not smart enough, but because the universe's structure prevents certain knowledge from being obtainable. Let's take one more breath before we finish this journey, considering what all of this means for the future and for how we live our lives right now. Whether or not we live inside a black hole, the quest to understand continues. New telescopes, new experiments, new technologies push the boundaries of what we can observe and measure. Let's look at what's coming and what it all means. The Event Horizon Telescope is being upgraded. More observatories are joining the network, increasing resolution, allowing us to see black hole event horizons in finer detail. We might watch matter fall in real-time, observe jets forming track changes in accretion disks. Each observation teaches us more about how black holes behave, potentially revealing clues about their structure and whether they could contain universes. The James Webb Space Telescope peers into the early universe, seeing galaxies forming just hundreds of millions of years after the Big Bang. These observations test our understanding of cosmic evolution, of how structure emerged from initial conditions. If our universe formed inside a black hole, early galaxy formation might show signatures of that origin. LISA, the Laser Interferometer, space antenna, will launch in the coming decades, detecting gravitational waves from space. It'll observe supermassive black hole mergers events too large and too far for ground-based detectors. Each merger tells us about black hole properties, how they grow, how space-time behaves in extreme conditions. Artificial intelligence is transforming black hole research. Machine learning algorithms sift through massive datasets from gravitational wave detectors, identifying faint signals humans might miss. Neural networks simulate black hole dynamics faster than traditional methods, exploring parameter spaces too vast for conventional computation. AI might find patterns we haven't thought to look for, revealing connections between observations and theory that human intuition misses. Like when you plan your future, you're simulating what hasn't happened, yet exploring possibilities before they become real. Quantum experiments probe the boundary between quantum mechanics and gravity. Researchers create analog black holes in laboratories using sound waves in fluids or light in special materials, studying Hawking radiation and quantum effects in controlled settings. While not real black holes, these analogs test principles that might apply to actual ones. But here's what we must accept: some questions might remain unanswerable. We might never know with certainty whether we're inside a black hole. We might never directly observe higher dimensions or travel to other universes. We might forever wonder about the singularity's true nature, or what happens to information in black holes. And that's okay. Not knowing isn't failure, it's the human condition. Mystery drives us forward, keeps us curious, prevents complacency. If we understood everything, what would be left to discover? If every question had answers, where would wonder go? Whether we're in a black hole or not, you're still you. Your life still matters. You're still part of something miraculous. Think about what this means philosophically. If we're inside a black hole, if reality is holographic, if multiple universes exist, does it change how you should live? Does it alter what matters? No, not really. You still experience joy and pain. You still love and lose. You still create meaning through connections, through work, through understanding. The universe's structure doesn't dictate purpose. You do. If we're projections from a two-dimensional surface, you're still conscious. If we're inside a black hole, in a higher dimension, you still have agency. If countless universes exist beyond our own, your choices in this one still shape your life and impact others. The cosmic perspective can be humbling, even overwhelming. We're tiny, living on a small planet, orbiting an average star in a vast galaxy, possibly inside a black hole, possibly one universe among infinite others. But we're also remarkable. We're matter that became conscious, that asks questions, that figures out we might be inside a black hole. That's extraordinary. This story has no clear ending because the universe's story continues. And that's the beauty of it: infinite mystery, eternal discovery. Not knowing everything means there's always more to learn. Mystery is a gift, not a problem. It means tomorrow might bring revelations we can't imagine today. It means the universe remains full of surprises. For practical life, this means be curious, ask questions, Don't accept easy answers. Be willing to change your mind when evidence changes. Stay humble about what you know and honest about what you don't. And find wonder, not despite the mysteries, but because of them. Whether we're in a black hole or not, we're here now, conscious and alive, able to contemplate these vast questions. That alone is miraculous. As this story ends, as your day ends, let these thoughts settle gently. Picture the stars scattered across the night sky, silent and distant. Picture black holes invisible, yet present, shaping galaxies across cosmic distances. Picture the universe vast and old and strange, containing mysteries we've barely begun to unravel. And picture yourself small, yet significant, a brief pattern of consciousness in an ancient cosmos, asking questions that might have no final answers, but are worth asking anyway. When you close your eyes tonight, let the vastness comfort rather than frighten you. Imagine you're floating gently through curved space-time, flowing like a slow river, carrying you softly toward rest. There are no boundaries, here no event horizons, no impossible questions, only the gentle dark, the quiet peace, the soft pull of sleep, drawing you inward like gravity that doesn't crush but cradles. Think of those distant stars burning silently across billions of light years. Think of black holes, patient and eternal, holding galaxies together. Think of the universe, whether we're inside one or not, indifferent to our worries, yet somehow making space for consciousness, for wonder, for you. Let those thoughts become dreams, and dreams fade into the peaceful nowhere of deep sleep, where nothing needs proving, nothing needs understanding, and you can simply rest. Whether you wake tomorrow inside a black hole or outside one, you'll still wake as yourself, still have this day, still be part of this strange and beautiful cosmos. Sleep now. The universe's mysteries will wait. They've waited billions of years already. They'll wait through your rest, through your dreams, ready for you whenever you're ready to wonder again. And if you wake tomorrow and discover we really are inside a black hole, well, at least now you understand it. At least now you know what it means. And that's something. Good night. Rest well. And thank you for wondering with me.